So we're going to review for the midterm. This video is going to have to be better than nothing. Been a frustrating technology day. So first of all, if you click on midterm in Canvas, you can find a list of the objectives that will be tested. I'm just going to work a representative example problem that tests that objective. That doesn't mean that the midterm is like that example problem. So for example, the first objective is find the volume of a solid formed by rotating a region about a given axis by using the washer method and be able to sketch the region. So I may choose to do one that may be rotating about X. The one on the midterm may rotate about Y. So you want to make sure you review, but I'm just trying to give you a good review of the basic topics. So as you're looking, we basically have the volumes by washer method, volumes by shell method, determining work, and then the rest of the midterm is on integration techniques because we've learned several. We've learned how to integrate by parts. We've learned how to integrate products of sines and cosines. We've learned how to use trig substitution to integrate. We've learned how to do partial fractions. We also need to be able to do any of the things that we'd learned before that may show up within these, which are trig functions, exponential functions, polynomials, natural logs, and u substitution. All of those could be a part of the ones that you were asked to integrate. So let's go ahead and get started with our first objective. And so we want to use the washer method to find the volume of a solid. So here we have y equals sine x plus 1, y equal 1, and x equal pi over 2 defining our region. So the first thing we're going to do is sketch our region. And so I know sine x normally would start at 0, but that plus 1 would shift everything up 1. So it's going to start right here. And I know its period is 2 pi. So I know at pi over 2 it will go to its maximum. And that's actually as far as we need to go. So our curve goes like this, and then our other boundaries are y equal 1 and x equal pi over 2. So there is our region. We're supposed to rotate this around the x-axis. So if we're using the washer method, we know that our slices are perpendicular to our axis of rotation. So our slice is going to go like this. So I see that's a little thickness dx. So the first thing I know is everything is going to be in terms of x. So my limits of integration looks like they're going to go from 0 to pi over 2. And now it's pi big R squared minus pi little r squared because we're rotating this around and we'll get a disk, and then we're going to subtract off the area of the hole. So basically we have the washer. So I'm going to put the pi out in front. So let's go ahead and look first of see what this would be down to our axis of rotation. That's our big R. So we can see that's just the y value of this function, which is sine x plus 1. So it's going to be sine x plus 1, and that's our big R, so that needs to be squared. And then we're going to subtract off the area of the hole. That's our little r. That's right here. And we see that's always going to be a 1. No matter where your slice is, you're always going to be subtracting off that 1. So that's 1 squared. So there is our integral that will give us the volume of that region. So let's go ahead and see what we can do to simplify. We've still got the pi out in front, and we've got 0 to pi over 2. We're going to FOIL this, so we're going to have sine squared x plus 2 sine x plus 1. And then we still have that minus 1, and then dx. So it looks like our 1's will cancel. Whenever we see a sine squared and we're trying to integrate, we're going to use the half angle identity. So let's go ahead and put that in. We know that that's going to be 1/2 and then 1 minus cosine 2x. Remember that the cosine squared x and the sine squared x half angle identities look the same, but one's plus and one's minus, and the sign is minus. Okay, we still have our plus 2 sine x, and that's dx. Okay, so now let's go ahead and do the integration. So we still have our pi out in front. If I distributed this through, this would be a 1/2, so that's going to be 1/2 x. And then this will have a 1/2 on it, and this is going to be sine 2x, but there will be a 2 generated by the chain rule, so I need the reciprocal of that, plus I had this half out in front, so the half times the other half, so that's why that's 1/4. Okay, then I have here going to be minus 2 cosine 2x, because the derivative of cosine is negative sine, but there was no negative, so that negative will take care of that. And then we're going to evaluate that from 0 to pi over 2. Okay, so we still have our pi out in front. If I put in pi over 2, I'm going to have pi over 4. Putting pi over 2 in this term, it's going to be the sine of pi, which is 0. Putting pi over 2 in this last term, cosine of pi over 2 is also 0. So then minus, we're going to do the lower limit. Well, I'm putting in 0, that's 0. 0 here is 0, but the cosine of 0 is 1. Times the negative 2 will be negative 2, and then it combines with that and makes that a plus. So this is the answer to our volume for this region. You want to leave your answers in exact form, so that's fine. If you needed to know it in an approximate number, you could punch it in a calculator and get an approximate, but we'll want just exact form on the midterm. So next objective is to use the shell method to find the volume rotating about an axis. And so let's go ahead and see what we've got here. Draw our region and see what we've got. So we have y equals 3x, so that's going to have a y-intercept of 1 and a slope is going to be up 3 over 1. So it's going to look something like that. And then looking here, we've got y equal 3, so that's going to come across like that, and x equals 0. So we can see there is our region. Now we're supposed to rotate this time around the y-axis. So we're going to rotate here. And we are supposed to use the shell method. So when I make my representative slice for shell method, it's parallel to the axis of rotation. So my shells are going to run like this. So it looks like we again have a little thickness dx, because my little slice there, if I'm looking, so everything's going to be in terms of x, and so my x is going to go from 0 to whatever the x value is right here, and I can figure out what that is, because that basically is, well, I mean, I can remember when we counted the slope, we went up 3 and over 1, but you could also figure that out because it's when the y is 3, so we could let the y be 3 here and solve this, and we would see that x equals 1. So my scale, this is my, these are bigger this way. I did that so it wasn't so squashed and we could see our region. Okay, so shell method, we need to take 2 pi r. And so if I'm rotating about the y-axis, then our r is going to be this distance right here to the shell, which is going to be x. And then we need to multiply that by the height of a shell. This little blue thing is representative of a shell, so how would I express that height? Well, I can see that it's all the way up minus this piece here would give me this piece right here. I'm going to put this in red. This is the height of the shell. So it looks like it's going to be 3 because that was the y value at the top, and then subtract off the y value of this line. So subtract off 3x. So the best way to do these is to look at the picture, look at your region, and see how do I need to express the height of that shell. Well, it goes all the way to the top, that's 3, but then it doesn't go all the way to the bottom, so I got to subtract off that y value. Okay, so now let's go ahead and see if we can evaluate our integral. So we have 2 pi, and then I'll go ahead and distribute this through. This would make this 3x minus 3x squared, and I'm going to integrate that. So that's going to be 3/2 x squared minus x cubed, and then that needs to be evaluated from 0 to 1. So it looks like I'm going to have 2 pi, and then this is going to be 3/2 times 1 squared minus 1 cubed. And then when we do the lower limit, those are both 0. So I've got 3/2 minus 1/2, or sorry, 3/2, I got ahead of myself, minus 1, which is 1/2, and then multiplied by 2 pi is pi. So the area of this region is pi. Okay, our next objective is to be able to find a variable force. So here we have a force of 10 newtons holds a string stretched 0.5 meter from its natural length. How much work will it take to stretch the spring 2.5 meters beyond its natural length? Okay, so first of all, for a spring, we have Hooke's law applying, and we have force equals the spring constant times the displacement. So they are telling me that when I apply a force of 10 newtons, that the displacement is 0.5. So that is so I can figure out what the spring constant is, and it looks like it's 20. So now I'm going to integrate, and I'm going to stretch it from its natural length, 2.5 meters. So those are my limits of integration. And it's the force, which is kx, so it's 20x, and then our little dx. Alright, so now I'm going to work the integral, so that's going to be 10x squared, and we need to evaluate that from 0 to 2.5. And so that's going to be 10 times 2.5 squared, and then the lower limit would be 0. And so that's going to be, looks like 62.5. And our units, we had a force of newtons and a length of meters, so they're Newton meters, which is joules. Okay, so those are our three objectives that aren't just integration strategies. They involve integration to do them, but now we're going to start with the integration strategy. So after you do those things, you're just going to see several integrals, and the directions will just say to integrate. So you need to have a clue of what you might try. So as I'm looking at this first integral, I see I have the product. And so I am thinking of integration by parts, because just looking at those, that's perfect form for that. I'm actually going to use tabular because this will work nicely for tabular. So you make a table and you put the two functions as the columns, and I differentiate till I get 0. So this is going to be 4x and then 4 and then 0, and I integrate this side and fill out the table. So this one's going to be negative 1/3 cosine 3x, because I need that reciprocal of what was generated by the chain rule, and the derivative of cosine is negative sign, but there was no negative, so I need that negative there to cancel it. Okay, integrate one more time, and I'll get 1/9 sine 3x. Again, I generate a 1/3 because I need to cancel that 3 from the chain rule. And last, I multiply, and I get 1/27 cosine 3x. Now applying our tabular, this is multiplied by a plus, this one by a minus, this one by a plus, and I'm ready to write my answer. I'm going to put it down below so I got room to write it out. So these would be negative 2/3 x squared cosine 3x, and the next one would be plus 4/9 x sine 3x, and then the next one would be plus 4/27 cosine 3x, and plus a constant. So there is our answer. Okay, let's go ahead and move on to the next one. So in looking at this one, I see that I have a polynomial over a polynomial, so I would definitely want to factor to see if it'll reduce, and then what I want to do from there. So this will factor into x plus 5 and x minus 1. Nothing reduces, so I see that I'm going to need to do partial fraction decomposition. So I'm going to write it down here. I've got x plus 3 over x plus 5 times x minus 1. And if I break that down, it'll be something over x plus 5 plus something else over x minus 1. Okay, we're going to clear that of fractions, so that's going to be x plus 3 equal a times x minus 1 plus b times x plus 5. And now we're going to conveniently, first we'll let x equal negative 5. So this side would be negative 2, and this would be negative 6a. So it looks like a is 1/3. And then we're going to let x equal 1. So that side's going to be 4, and that's going to be 6b. So b is going to be 2/3. Now that I have those partial fractions, I can express this integral breaking that up. The first one's going to be 1/3 over x plus 5. And then the next one is going to be 2/3 over x minus 1 dx. Now we can go ahead and do the integral. The 1/3 will just be in front, and so integrating 1 over ln of x, or sorry, of 1 over x plus 5, got ahead of myself again. This is going to be the natural log of x plus 5, plus we got 2/3 natural log of x minus 1, and plus our constant. So there's a good example of working a partial fraction decomposition. Okay, let's go ahead and move on to the next one. As I look at this one, I see the product of trig functions, so I'm hoping that at least one of these is odd, and it is. So I'm going to express this as sine to the 4th x cosine squared x and split off a cosine x dx. That way I can do u substitution and let u be sine x, and then my du is cosine x dx, and I've got that right there. So I can go ahead and do the substitution. Sine to the 4th becomes u to the 4th. Now I have a cosine and I'm trying to substitute in sine, so I'm going to use the Pythagorean identity and replace that with 1 minus sine squared x. So now I can replace that with 1 minus u squared. And then my cosine x dx just becomes my du. So if I went ahead and distribute that through, that's u to the 4th minus u to the 6th du. And so I'm now ready to do the integration. That's going to be 1/5 u to the 5th minus 1/7 u to the 7th plus a constant. And then finally resubstitute. Remember, u was sine x, so I've got 1/5, and this is sine to the 5th x minus 1/7 sine to the 7th x plus a constant. So there's a product of trig functions. Okay, now in looking at this one, nothing reduces. I'm having a look at that, and it's lending itself to saying let's draw a triangle, and we will set up some kind of a trig substitution. I need one of the sides to involve a 1 plus x squared. Now this doesn't have a square root over the top, but that's okay. It's still going to be using, this side's going to be 1 plus x squared square rooted if this one's an x and this one's a 1. So there's my triangle, and tangent of theta is going to be x over 1. So there's my substitution, and I need dx, and dx is secant squared theta d theta. Okay, I have everything set up now to do the substitution and get this in terms of theta. So I need to take the 1 plus of the x squared part and replace it with tangent squared theta. And then it has a squared on that, and then I need to replace the dx with secant squared theta d theta. Okay, so there's my substitution. Well, as I'm looking here, 1 plus tangent squared is secant squared theta, and then that's squared. And so one of the secant squareds in the bottom will cancel with the one on the top, so it's going to leave me 1 over secant squared theta d theta. Now if we look at that to think how would I integrate, well wait a minute, what does secant squared mean? It means 1 over cosine squared. So it's 1 over cosine squared, so when I flip it over I just have, let's have the integral, cosine squared theta d theta. So we got it down to cosine squared theta d theta to integrate. Well, that's telling me half angle then, because I need to get it so it doesn't have a squared. This one's a cosine, so it's going to be a plus between them. Okay, so now I have it down to something that I can integrate, and if I want, I can move that half out of the way, put it out in front. So let's go ahead. That's going to be 1/2. Integrate 1 is going to be theta. Integrate cosine 2 theta, well that's going to be sine 2 theta, but we need to have a 1/2 on there because the chain rule would have generated a 2. Okay, and now we've got that plus a constant. We're not done because I need to get everything back in terms of x, and I'm going to use my triangle to help me do that. Now up here, if tangent theta equals x, then theta is going to be inverse tangent of x. So that's what I'll do to replace this theta, but this one is sine 2 theta, and my triangle is in terms of theta. So I'm going to use the double angle identity and write out what sine 2 theta is. And sine 2 theta is 2 sine theta cosine theta. Okay, these are identities you need to know because they show up a lot in this kind of integration, both the half angle and the double angle. Now it looks like those 2's will cancel, and now I'm ready to use the triangle to get things back. And so I have my theta, that's inverse tangent, so that's tan inverse of x. And then I have plus, and the 2's canceled here, so I need sine theta and I need cosine theta. So I'm going to go back to this triangle. Sine theta is opposite over hypotenuse, so that's going to be x over square root of 1 plus x squared. And then that's multiplied by cosine theta. Cosine is adjacent over hypotenuse. And then I need my plus a constant on the end. Now, one last thing is I can combine these, and the square root of 1 plus x squared times the square root of 1 plus x squared will get rid of the square root sign. So I'm trying to figure out where I'm going to put the answer. I guess I'm going to squish it in at the bottom. I'll put it in red so it stands out from what I'm squishing it with. So this is going to be 1/2 tangent inverse of x plus x over 1 plus x squared, and then plus a constant, because our two radicals combine to get rid of the radical. So there's a good example of a trig sub. You want to review all the trig subs that we've had, because it doesn't necessarily mean that on the midterm it's going to be a tangent. I just picked a problem that involved trig subs so we could look it over. It might involve tangent, might involve secant, might involve sine, so you'll want to review those. Okay, let's go on to our next one. Okay, as I'm looking here, this one suspiciously looks like it would be an integration by parts. It's not. But I want to show you what would happen if you went to try that, so you could realize that if you didn't see it already. If you went to set this up and did 2x squared and e to the negative x cubed, yes, you could fill out this column and get that down to 0, but we don't know how to integrate e to the negative x cubed, because when you're trying to do that, because the thing inside of the e is negative x cubed, it would have needed an x squared term, because the chain rule would have generated an x squared term. Oh, well, wait a minute. But the original problem had an x squared term. So that leads me to see that this would be a u sub and would work very nicely if I let u be negative x cubed. Because then du would be negative 3x squared dx. And guess what? I have the variable that I need. I have the x squared piece. So I don't want to deal with the 2. And I'm going to need to divide this then and make this a negative 1/3 to get rid of that. But I can replace then x squared dx with negative 1/3 du. And I'm going to do that. So 1/3 du. And then this other part is just e to the u. So this one was perfectly a u sub. And the thing about it is that e to the function inside, its derivative function was sitting out in front. Now it's off by a constant, but as long as you've got the right function of x, in this case an x squared, then it's going to work, as you see. Okay, so now we can go ahead and do the integration. Well, this integration is pretty easy, and then plus a constant, and then we're going to resubstitute. So negative 2/3 e to the negative x cubed plus a constant. Now this one would be really easy to check because you're better at differentiation than integration, so take a derivative of that and make sure you get this back. So if we take a derivative of that, we would have the derivative of e to the negative x cubed, I just had this constant out in front, is e to the negative x cubed times the derivative of the negative x cubed part. So if we took that derivative, and of course the derivative constant is 0, looks like the negatives would cancel and the 3's would cancel. We'd have 2x squared e to the negative x cubed, and that's exactly right. Okay, let's go ahead and go on to the next one. So in looking at this one, as I'm looking at it, I'm going, ooh, is that kind of like the last one? But the problem here is inside of the e is negative 2x, and the derivative of that's negative 2, not a function of x that I see right here. So instead, that's leading me again to an integration by parts. I'm going to do 3x and e to the negative 2x, and then this will be a 3 and a 0. This will be e to the negative 2x, and I need the reciprocal of that power. And then e to the negative 2x, and I need the reciprocal there again, so that'll make that one a 1/4. Okay, so this makes this a plus, this one a minus. This time we have a definite integral, so it looks like I'm going to have negative 3/2 x e to the negative 2x and minus 3/4 e to the negative 2x, and that needs to be evaluated from 0 to 2. Alright, so that's going to be negative 3/2 times 2 e to the negative 4x minus 3/4 e to the negative 4x, and then lower limits. If we put in 0, that one will make that 0, but putting 0 in the other one, I'm subtracting because it's the lower limit, and that'll be 3/4 e to the 0, which of course is 1. Okay, so let's see what we've got. These will cancel, and it looks like I have negative 3 e to the negative 4x minus 3/4 e to the negative 4x, so those can combine. This is negative 12/4, so negative 15/4 e to the negative 4x plus 3/4. That negative kind of sunk there. Let's move it up. Okay, so there's our answer. Okay, let's go ahead and move on to the next one. So in looking at this one, I see a polynomial over a polynomial, so the first thing I'm going to do is factor what I can. This will factor by pulling an x out and leave me x squared plus 9, which does not factor anymore. So this one is a partial fraction decomposition. So as we set this one up, I'm going to have x plus 2 over x squared plus 9, and so our partial fractions are going to be a over x plus, because this denominator is an irreducible quadratic, then I need to have two terms in the numerator, so I need a bx plus c. Let's go ahead and clear the fractions. So I have x plus 2 equals, and I'm going to go ahead and multiply it out, ax squared plus 9a plus bx squared plus cx when I clear this of fractions. So I am going to equate coefficients. I'm first going to look at the x squareds. There's no x squareds on the left. There's an a plus a b on the right. Now I'm going to look at the x's. There's 1 on the left and there's a c on the right. Now I'm going to look at the constants. There's a 2 on the left and there's a 9a on the right. So I already know c, and it looks like a is going to be 2/9. Well, then I already know b, because that's got to be negative 2/9 if I put 2/9 in here and solve that. Okay, so here are my coefficients. So this will break down into a, which was 2/9 over x, plus negative 2/9 over x, plus 1 over x squared plus 9. Okay, and then this is dx. So now that we have it broken down, we want to see what we need to do to integrate. And I've got the first term down, but the next one I'm going to need to split up. So I'm going to need some more room. So I'm going to erase the steps where I found the partial fraction. So if you need to see those, you can pause the video and watch it or rewind. But they're going away so that I've got room. Okay, so the next thing that we want to do is we want to see if we can break this up into 3 different fractions, because I see I have the numerator has 2 terms here. So we're going to break that up. We're going to have the integral of 2/9 over x minus 2/9 x over x squared plus 9, and then plus 1 over x squared plus 9, and that's dx. Okay, now we're ready to look at each fraction and see if we can work those out. So I can do this one. That's going to be 2/9, and if we integrate 1 over x, that would have been natural log of x. Okay, looking at this one, I can see it's a nice U substitution because in the denominator it's x squared plus 9 and its derivative is 2x, and I've got that in the numerator. So for that one I'm going to let u be x squared plus 9. That means du is 2x dx, and so if I'm replacing this, that's going to be negative 1/9, and I'm just going to put that first, and then this integral, and I'm leaving the 2x part and the dx here. So the 2x dx becomes du, and then I just have 1 over u. So I can see that's going to be negative 1/9 natural log of u, but I'm going to go ahead and replace that back again so we got room here. So this would have been ln u, and then there's my u. Okay, now we're ready to do the third one, and you've got a couple of options here. You can, look at this to doctor it up to get an inverse trig function, and if you don't see that, you can draw a triangle. So I think I'm going to draw the triangle first, and then let's talk about what I just meant by that. So I can draw a triangle here, and I can make this one x and this one 3, so that when I find the hypotenuse, it's going to be the square root of x squared plus 9. Here's my theta. So I'm going to have tangent theta is going to be x over 3. So x is going to be 3 tangent theta, and dx is going to be 3 secant squared theta d theta. Alright, so we'll go over here to the left bottom to work this. So if I was doing the integral, I'd have 1 over x squared. That's going to be 9 tangent squared theta then, and then plus 9, and then dx becomes 3 secant squared theta d theta. Alright, let's see what we can do with that. I can factor a 9 out here, and that would leave tangent squared theta plus 1, and in order to fit it, I'm going to go ahead and replace that already. So we factored a 9 out, and then the tangent squared theta plus 1 Pythagorean identity became secant squared theta. Okay, so that replaced that. Oh, well then this secant squared will go with this secant squared, and then this 3 will reduce with this 9. So I just have 1/3 and then just d theta, so that becomes theta plus a constant when I integrate that. Okay, finally then I have 1/3, but what was theta? Well, here was my connection, so theta would be tan inverse of x over 3. So this is going to be tan inverse of x over 3 plus a constant. Now, if you wanted to, you could have expressed this so that you could see that x over 3, and you could have taken that denominator and factored a 9 out, and I'm trying to see where I can fit that. So I'm going to, again, let's see. I've got the other piece of this, so this actually goes with this. Sorry, I shouldn't have just circled that, because this is the first two terms, and then there's the next one down there. Bad order, but just so I could fit it all. Okay, I'm going to go ahead and erase the partial fraction piece right here so that I can show you what I'm talking about. Okay, so if we get this out of the way, if we're looking at this particular that was 1 over x squared plus 9, I can actually take that and I can factor out a 9. Okay, so if I factor out a 9, well, since it didn't seem to factor out of the x squared, I could write this as x squared over 9. That way, if I multiplied it back through, it would be x squared, and this would be plus 1. Well, thinking of inverse tangent, if I have 1 plus, now we still have this 1/9 here. Alright, so I can express this as x over 3 squared. And then I could recognize it as an inverse tangent of x over 3. But the stuff inside the tangent is x inverse tangent is x over 3, which would generate a 1/3 from the chain rule. So we'd need the reciprocal of the 1/3, and that will cancel with the 9, and so we do get this answer. Now if that's hard for you to see, it's totally fine to do the trig sub, but for those of you that kind of want to set it up and see the inverse tangent, that works as well. Okay, let's go ahead and move on to the next one. Okay, as we look at this one, I see secants and tangents, so I want to split something off so that I can do U substitution. But on secants and tangents, it's not splitting off one of the odd ones, I need to split off a derivative. Well, the derivative of secant is secant tangent, so I can split off a secant and a tangent if I want to let U be secant. Or the derivative of tangent is secant squared, so I could split off a secant squared. And I am going to do that. I'm going to split off a secant squared. So I am going to let my u be tangent x so that my du is secant squared x dx. So let's see if that's going to work here. When I split it off, I'm going to leave me a secant squared x and a tangent cubed x, and then the secant squared x dx. Now I have limits of integration here as well that I've got to watch for, because if I do a u substitution, I've either got to get them in terms of u so that I can evaluate them, or I've got to do it as an indefinite integral and get it integrated and then get it back in terms of x and then evaluate them. So I think we're going to do a u sub, and we are going to go ahead and change the limits. That's probably the easiest. So my secant squared, I need to replace that with 1 plus tangent squared x, and now I can write that as 1 plus u squared. And then tangent cubed is u cubed, and then this secant squared x dx is my du. Now, changing my limits of integration, I had 0, so I put in the tangent of 0 to find out what my u is, and that's 0. And then I have pi fourths. Well, the tangent of pi fourths is 1. So I changed my limits of integration to get them in terms of u, and now I'm integrating from 0 to 1 of u to the third plus u to the fifth du. Now it's down to something easy to integrate. That's going to be 1/4 u to the fourth plus 1/6 u to the sixth, and that's going to need to be evaluated from 0 to 1. So that's going to be 1/4 plus 1/6, and the lower limit are both zeros. Okay, so let's see, that's 3/12 plus 2/12, so it looks like that's going to be 5/12. Okay, let's go ahead and look at another one. So here we have the integral from 1 to e of x squared ln x dx. Okay, and looking at this one, I see I have the product and it involves an ln x. So remember that when we do integration by parts and we involve an ln x, that's always our u. Why? Because I know du, it's 1 over x, and then I get rid of the ln part. But if I had called that one, I didn't call that one my u, then I would needed to call it my dv, and I would need to be able to integrate that, and we don't want to go there. So we're going to set up integration by parts. U is going to be ln x, so dv is going to be x squared dx. So now my du is 1 over x dx, and my v is 1/3 x cubed. Now I can go ahead and substitute those in. Now we still have to remember that when we're done, we're going to need to evaluate this from 1 to e. Okay, so remember our integration by parts formula says if you're integrating u dv, that is going to be uv minus integral of v du. So that's just the form you can to help you memorize it. So let's go ahead and apply that. So I need uv, so that's going to be 1/3 x cubed natural log of x minus the integral of v du, Well, that's going to be 1/3 x cubed, and then multiply it by 1 over x dx. Now remember, we have 1 to e, so this would need to be evaluated from 1 to e as well. Okay, so now this will cancel and leave me an x squared here, and I need to do that last integral, and then I'll be able to evaluate. So I have 1/3 x cubed natural log of x minus, integrating this, it's going to need a 1/9 and going to be x cubed because I need one higher power. I need the reciprocal of that power, and so that was 1/3 times by the 1/3 that's already there. Now all of that needs to be evaluated from 1 to e. So that's going to be 1/3 e to the third natural log of e minus 1/9 e to the third minus, now if we put a 1 in here, the natural log of 1 is 0, so that whole term is gone. So this will be a plus 1/9, putting in that 1. Okay, natural log of e is a 1. So let's see what we can combine. I have 1/3 e to the third minus 1/9 e to the third. Well, that's 3/9 minus 1/9. So it looks like I have 2/9 e to the third plus 1/9. Okay, so that covered our objectives. You'll want to work some more. Those integration strategy, the worksheet that I posted is a good practice, and I also posted a key. Those would be great to practice, and then make sure you review your volumes by washer and shell and your work as well. I will also be monitoring to answer any questions, so feel free to email me if you have any questions either about the midterm or you're working on something or reviewing and you have a question, because I'm here to help you and I want you to have a great midterm.